My name is James McNanny, and my partner was Colin Allen. And our final project for ELEC 327 was the game of life, but in 3 dimensions. We got our inspiration from Joseph Conway's Game of Life, a cellular automaton, and we thought that it would be an interesting implementation both of the modules and the skills we learned this year in ELEC 327. We added challenge to ourselves by forcing us to implement the game of life and the hardware in 3 dimensions using a cube. And we also allowed for user input by interfacing with the initial states of each cell using a button array. Something we did not expect but was rather interesting was the unique simulations that having 3-dimensional neighbors and corners that only have 7 neighbors provided. When approaching how we wanted to format the array of LEDs on the cube, since we were using SPI communications, we were treating the LEDs as one single long chain. And to be able to map those into 3-dimensional space, we used a zigzag pattern per face, which would allow our first LED to be in the top right and our last LED for the face to be in the bottom right. This would allow for a short connection between the interfaces of 2 faces. And by flattening the cube into its net, we were able to plan out how we would want to arrange the faces next to each other, as shown. With 5 buttons per face and 6 faces, totaling a total of 30 buttons, we needed an intelligent way of being able to interface with buttons specifically, but also without being too hazardous with just throwing traces around. Our result was having 5 traces going vertically and 5 traces going horizontally, where each vertical trace was connected to one and only one horizontal trace, which would correspond to a specific button. For example, button 1 could be connected to this far left and top trace, and it would only be allowed to communicate through one of those traces. Why this is important is whenever we interface 2 faces together, if we want the same corresponding left button or top button to be able to be read by the MSP, we would want it to be able to be accessed from the same pin. And going across interfaces or faces of the cube without having to use too many inter-wire connects or floating wires, having very specific arrays that we can then layer against each other so that each button could just be connected to the same vertical or horizontal trace using one jumper wire was very important for us. Seen here is the schematic we used for each individual face of our project. And since we were thinking about it thoughtfully, we were able to replicate the same exact face for each of the 6 faces of the cube. Seen here is our array of LEDs, which is what the MSP 430 is going to see, is not a grid, but a single, essentially, row of LEDs. And this was our final PCB design. The MSP 430, seen in the top right, would communicate with the first LED on the grid. The buttons are connected to vertical and horizontal traces, and we were able to route out the signals that would be necessary to interface across the faces in a very comprehensible manner. Because we were so thoughtful with how we prepared our PCBs, the interconnect between faces was very comprehensible and very clean. Seen here is the data and clock interface across faces, data in and data out, clock in, clock out. And these 5 wires show the connect between buttons, and these 2 wires are for power and ground, totaling a total of 9 wires between faces and allowing for something clean and very easy to debug when necessary. After bringing together all 216 LEDs, 30 buttons, MSP 430, and interconnect within the cube, we were able to create this final product, which we were very happy with because of our foresight into how we connected the faces together. We were able to compactly compress it and keep all of the wiring very clean and neat, internal of the cube.
This project really was an accumulation of all that we've learned so far in ELEC 327. Some of the major concepts that we used in previous labs that we were able to apply to this were interrupts, SPI communication, low power modes, polling, timer modules, overall system architecture of our program, and then one of the more important new concepts that we were exposed to in this project was more intensive memory management, and we had not been exposed to that in previous labs. Interrupts were really important in this lab. We had 30 buttons distributed across the cube, many of which were in parallel to deliver 5 different signals coming into the MSP430 as user input. We used interrupts to pick up whenever these buttons were clicked, and to use that in our control logic as to selecting the initial state of the simulation. We also had an interrupt for timer A to use as a counter variable. SPI communication was really important in this lab because it was how we communicated with the array of 216 LEDs. We did this at various points in our code, from the initial setup when we're selecting bits to throughout the simulation. And then every time that we needed to send a signal to the array, you start by sending an initial start sequence of 4 different bytes of zeros. Then you send 4 bytes for every LED, the brightness, and then the specific color that you would like, and then you're sending an end signal that's 4 bytes of just ones. You can only send 1 byte at a time due to buffer constraints, so we use polling to wait for the flags to be set based on when the LED was ready to process the next byte of data to send all this data to the 216 LEDs. To save on memory, we made the LEDs either off or a consistent value so that we only needed to keep track of the state of whether an LED was on and off and not a particular color. Low power mode was also important because we wanted to use the technique of turning the CPU off to wait for interrupts from the buttons. This was helpful for waiting a variable amount of time for the user to hit the next button for that to determine what the next control process is in terms of moving the LED around for selecting. And by turning the CPU off, it saves power and is a convenient way to wait for user input. We use an idle period, so a certain amount of time since when the user has last pressed a button, as the way to start the simulation. We used timer A to keep track of this, so every time a button was pressed, it would reset timer A, and then timer A would decrement, and there would be a check whenever it would hit the interrupt that if it got below a certain threshold, it meant to leave the control flow and enter the simulation itself. In this way, timer A acted as a pseudo watchdog timer, where the watchdog timer was getting reset every time a button was pressed. We decided that this usage of an idle time from when the last button was pressed was a convenient and intuitive way for the user to interact with the cube. Rather than having another button or component to keep track of in hardware and code, we simply let the user sit and wait without pressing a button for a short amount of time, and that signals to the cube that the simulation should start. Extending past the individual techniques that we've learned from previous labs, this project is really an accumulation of all of our coding experience in embedded systems. With that in mind, we tried to have thoughtful program design to make our code easy to debug and more intuitive to understand. One of the main ways that we did this was we separated our code into different functions to reduce redundancy and make it easy to understand when a particular function is occurring. One of the new challenges that we ran into in this project was more intensive memory management. The MSP430 only has 512 bytes of RAM, which is not enough to store 4 bytes per LED for the color and brightness as we've done in previous labs using SPI communication. It's not even enough to store a single int for every LED. So we needed to come up with a more clever way of storing the current state and next state of the LEDs in the simulation, as well as keeping track of the 8 neighbors of every LED in the simulation. We realized that the neighbors, as in the index into the array of every one of the 8 neighbors of a single LED on the cube, are values that we only need to read and never write to, as they stay constant throughout the simulation. By labeling the hard-coded array of neighbors as a const, we were able to tell the compiler/linker to store that array in the 16 kilobytes of onboard flash rather than in RAM. This had plenty of memory to store all the values that we need and freed up RAM for other usage. It was more challenging to come up with a solution in how to keep track of the current state and next state of the LED chain. The issue here was that we needed a single bit for the current state and a single bit for the next state, but C does not provide any good way of keeping track of individual bits in a bit field, so we had to come up with our own. Since there are 216 LEDs, each of which needs a single bit for a single state array, we decided to keep track of that in a 14-long array of unsigned integers, where every unsigned integer is size 16 and keeps track of 16 of the individual bits. The way that you index into this array is you divide the index of the bit that you're looking for by 16, and because it's integer division, it rounds down, and that gives you the index into this array of unsigned ints. And then you do modular arithmetic to get the remainder of the index, and that gives you the particular bit inside of that particular unsigned character in the array. A simple example here with size 6 arrays is if I wanted to access this 1, which is the 8th index, I would do 8 divided by 6, which is 1, so that would tell me that it's the first array. And then I would do 8 mod 6, which would give me 2, which would give me the index into this array where the bit is stored, 0, 1, 2. This was an intuitive and relatively straightforward way to implement storing a bit field, but it took quite a bit of thoughtful coding to figure out how to do it. We also performed the division using bit shifting and the modular arithmetic using logical AND because it was much more efficient for the processor. This is the code that we would use to actually access or set a particular bit in the field, where we divide by 16, perform modular arithmetic, move a specific bit to that location in the array, and then perform an AND to get the value of that single bit. This is our final cube. You can see that various LEDs are glowing bright blue while others are off as it's running the simulation. I'm Colin Allen, my partner is James, and this has been Life in 3 Dimensions.